This is the second part of the lecture on natural deduction for predicate logic. In the first part we saw the language of formulas for predicate logic, but we didn't actually get to natural deduction. So like in propositional logic, natural deduction is going to provide us with rules for reasoning in predicate logic. But we still have a little bit more work to do before we get there. So where we got to last time was the last thing we did was the notion of a sentence. So a formula is a sentence, you'll remember, if no variable occurs free in it. And the point of a sentence is it expresses a proposition that's either true or false independently of there are no free variables that we need to give interpretations to. So for example, we had the sentence for all x, if x is greater than or equal to 0, then it's a square number. And as we already commented earlier on, that sentence is true in the real numbers, but false in the rationals and false for the integers too. So sentences express truth values. What about formulas that do have free variables? What they express is relations on their free variables. So this formula here has a single free variable, x, two occurrences of it, but just one free variable, x. The variable y is bound. So it expresses a predicate on x, or a property of x, if you like. And that's the property that if x is greater than 0, then it's a square number. So in the real numbers, that property is true for all numbers x. Every number x satisfies if it's greater than 0, then it's a square number. In the rationals, it is true for those numbers x that are either negative, in which case they vacuously satisfy the implication, because x is greater than or equal to 0 is false, or they are rational numbers whose square root is also a rational number. And similarly, in the integers, it's the property of those x's that are either negative or are positive square numbers. So square numbers in the sense of being a square of an integer. Okay, so that's what formulas with free variables represent. In general, they express relations on their variables. So let's look at some manipulation that we would often like to do with such formulas. So we might consider a property such as, well, let's just take again being a square number, but we might just consider the formula x equals y times y. This has two free variables, so it's expressing a relation between x and y, and that relation is that obviously x is the square of y. But when we have such formulas expressing relations between variables, it's sometimes useful to specialize them by saying we're not just concerned with an arbitrary x here, but we want an x of a specific form. So for example, we might want to say something like x plus z. Or even x plus y, say, is y times y. That's an interesting relation between x and y, which in the integers, for example, is satisfied if both x and y are 2, but in general it expresses the relation between x and y. That is how you read that formula, so that the sum of x and y are equal to the square of y. So that's an interesting relation between x and y. But we've derived this second formula in a kind of uniform way from the first formula by replacing x with x plus y. So if we call this formula phi, maybe I'll put this in a different position actually. Let's rub that off. So if we call this first formula phi, oops, that's not a very nice phi. It looks like an empty set, but anyway, it's the Greek letter phi, the formula. And the second formula, well, we get it by taking phi and replacing the term x, with the variable x rather, with replacing the variable x with the term x plus y. So this we're replacing all occurrences, there's only one of the free variable x with the term x plus y. And this is a general operation called substitution, which one can perform on a formula and substitute all occurrences of a free variable x with any term. Okay, so from what we've written here, it looks like substitution is very simple. You simply replace the variable x with x plus y, but it can become a little bit more subtle, because suppose we look at another formula. So let's turn the formula, let's add a quantifier here. There exists a y such that x equals y times y. So whereas the first formula expressed a relation between x and y, this formula now only has one free variable, x, and so it expresses a property of x. And that property is, of course, that x is the square of some number. So x is a square in the structure that we're interpreting it in. So if we're interpreting it in the integers, this will apply exactly to the usual whole number square numbers, which are all non-negative integers, 0, 1, 4, 9. They'll all satisfy these properties. But the point is, it is a property just of x, not of x and y. So let's call this phi prime. So it's saying, well, let's just interpret in the integers. So in that we can say this property is expressing that x is a square number. So again, we can perfectly well substitute x plus y for x here. And what we mean by that is we want to say that x plus y is a square number. So that's what we want to say by, we substitute x plus y for x. So x plus y is a term, and we're substituting it for every occurrence of the free variable x. Then we want to have the formula saying that x plus y is a square number. But notice we can't simply now replace x here with x plus y, because if we do that, we'll get the formula that there exists a y such that x plus y equals y times y, which is not true for all square numbers. And the problem is that here we want to talk about x and y, and in order to do so, we can't, when we put the y inside, we can't quantify over it, because we're talking about some x and y that we're referring to here. We want to say x and y, whatever their values are square numbers. So the correct thing to do in this case is to rename this variable y appearing here, because the formula saying that x is a square number, it doesn't matter what we call this variable y. This formula could perfectly well be written as there exists a z x equals z times z. And now, if we do that, there's absolutely no way. So we view this as kind of basically the same formula, because what you call a bound variable doesn't actually affect what the formula says. But if we write the formula like this, we can perfectly well substitute x plus y for x without any ambiguity, because if we do that, we get the formula there exists a z such that x plus y equals z times z, which indeed says that x plus y is a square number. So this is the wrong substitution here. Let's put a big cross by it. Looks like an X, but that's basically saying this is the wrong substitution. This is the right substitution. So the trick in general, that was supposed to be a tick. There we are. The trick in general is that to substitute a term for a variable x, you need to firstly rename any bound variables in the formula so that those bound variables are different from the variable x you're substituting and are also different from any variables that are contained in the term you're substituting. So here we have the variable, so here y was different from x, but it wasn't different from the variable y that appears in the term we're substituting. So we need to rename it to avoid that clash, and we renamed it. It doesn't matter what we rename it to as long as it's not x or y, so we could have called it w, but we called it z. Okay, so that's a little bit of a fussy operation. So let me write it down in general. We can put it at the bottom of the page here. So substitution. I'm going to use the same notation as in the textbook. So that's in a formula phi. We substitute a term t for all occurrences of a free variable x. So in formula, let me write that, in phi, substitute t. So we're for free occurrences of x. Now one can give a precise mathematical definition of this, and it's actually rather unwieldy. That's rather awkward to deal with. It's actually quite easy to make a mistake in doing so, but the way that one performs substitutions in practice is rather easy to describe more informally, so I'm going to describe it like that. So step one is rename bound variables in phi, if necessary, so including that where they appear in the quantifiers. So they are different from x, and from all free variables, or all variables in T. You can't bound a variable in a term because a term can't contain quantifiers. So from all variables, only formulas contain quantifiers. And once we've done that, Then once you've done that, then you can just simply replace all free occurrences of x in phi with the term t. So replace all free occurrences of x in phi, but by which I mean the renamed phi. So replace every free occurrence of x with the term t. So that's exactly what we did above. So when we were substituting the term x plus y for the variable x, for the free variable x, we first renamed the bound variable y, so it was different from x, which it already was, and different from the variables in the term. So in particular, it needed to be different from y, so we chose z. We renamed the bound variable, so we need to change all the y's to z. And then we were in a position to simply replace the variable x with the term we're substituting in, x plus y. And that gave us the right meaning that instead of saying x is a square number, we were saying that x plus y is a square number. Okay, so having now got substitution to hand, the tool we can use, we can finally get on to natural deduction. And I'm going to do it by introducing the rules and giving example proofs as we go. And let's actually start with an example proof. So what I'm going to do is give you a natural deduction proof of a sentence, which is a valid sentence, so one that is simply logically true, so it's true independently of the meaning we assign to predicates. So I'm going to give a natural deduction proof of the following. So a natural deduction proof of a nice valid formula in predicate logic, which is that if we have unary predicates P and Q, unary means they take one argument, they have arity 1, then we have the following valid formula, logically valid formula. So it says that if P holds for all x and Q holds for all x, then then for all x we have that as a bracket, we have that both Px and Qx hold. Okay, that seems very simple if you think about it, but it's not immediate from the symbols themselves. It's immediate if we think about that it's true. So let's prove it in natural deduction. Here, the left-hand side has this priority, so the and is, so that both formulas on the left are the left side of the implication. The conjunction is the left side of the implication. So the first useful thing about natural deduction in predicate logic is that the rules for the propositional connectives are just the same as natural deduction from propositional logic. So we already know the rules for and, implies, negation, that's not, disjunction, that's or, and so on. So in particular here we want to prove an implication, so we're going to do that the way we were doing in propositional logic. So our first step is we're going to assume the left-hand side of the implication. So we're going to have the assumption for all x, px, and for all y, for all x, qx. So this is an assumption. Now, to revise a bit of the rules for propositional logic, when we've got a conjunction, we can apply the elimination rules on the left and the right. And, well, because we've got the conjunction here, we've assumed that if that assumption holds, then we can also derive that each of the conjuncts holds. So for all x, px holds. So this is by and elimination 1 on the left hand side from line 1. And we also have that for all x, qx holds. So that's by and elimination 2 from the first line of the proof. So we've got that far, but we want to show that for all x, px and qx holds. So how do we do that? Well, there's a natural method of proof. We are reasoning with natural deduction. There's a natural method of proof to show universal quantification. We want to show that for all x, px and qx hold. So we'll show that for an arbitrary x, px and qx hold. So in the next step, what we do is we give ourselves an arbitrary variable standing for an arbitrary value that we're going to show holds. To avoid confusion between the variables x that we're using in the formula and this arbitrary value, I'm going to call it y. And I'm following the textbook here. Their notation for this is when you introduce an arbitrary variable, you write it down just on the left-hand side here. So I'm introducing an arbitrary variable y. And introducing, if we've got an arbitrary variable y, so standing for an arbitrary element, from for all x, px, because p holds for all x, it in particular holds for y. So if we introduce a y, and then from the universal quantified formula here, we can derive that p holds for y. And that is actually the elimination rule for the for all connective. And that's then we're eliminating from the second line of from the formula in the second line of the proof. That's a 2. So maybe we'll go and write the rule down on the next page. So the elimination rule for universal quantification is if we have a formula for all x phi, doesn't matter what the formula phi is, but it's universally quantified for all x phi, so it's universally quantified. Then, and this was our reason for introducing substitution, so if phi holds for all x, it holds for any value of x we can supply. And any value for x we can supply can be given by any term whatsoever, a different variable y, or some other term like y times z, or something like that. If you've got some function symbols, you can build up complicated terms. So any term will represent some possible value, because phi holds for all values, it holds for arbitrary terms. So from the premise, that's what we're assuming to apply, that what we've already derived before applying this rule. If phi holds for all x, it in particular holds in the case that we instantiate by substituting any term t for the free variable for the free occurrences of x in phi. So here we remove the quantifier, we then look to see what the free occurrences of x are. So it's the free occurrences of x in phi, not in for all x phi, because that for all x phi has all the occurrences of x in for all x phi are bound. But this is the free occurrences of x in phi. And this is called for all elimination. Okay, so let's continue with our proof. So we've concluded that maybe go up, rub those dots out. Trying to get the pen. Right. So we've got P holds for y, but also by line 3, Q holds for all x. So in particular, that one holds for y as well. We already have the variable y available. We don't introduce it twice. We introduce it once. We've already got y, so we can, but still y is a term. So we can substitute y for x in the formula qx, and there it's simply replacing x with y. So this is again for all elimination, and this time it's from line 3 of the proof. And now we're in a good position because now we've derived, oh sorry, this should have been q of y, because we were eliminating from line 3 of the proof. So let's correct that. So now we can apply our introduction rule for the conjunction. And derive that px, py, and qy. So this is by and introduction. Sorry, not a. That's an and. So and introduction from lines 4 and 5. And we're now in a position to derive for all x, px, and qx for the following reason, that we have shown that py and qy is true for an arbitrary y. Remember, we were introducing here an arbitrary y. And the and introduction rule says, sorry, not the and introduction rule, the for all introduction rule says that suppose we have proved phi for an arbitrary y. This is a y, if I can get it there. So if we prove phi for an arbitrary y that we've introduced somewhere, then we can prove for all, this is going to be an x, for all x phi. Now there's something a little bit fishy at the moment which we need to correct. So here phi is a formula that Maybe I'll just try to make that a bit neater as well. Phi, because I do want the rules to at least be readable in the end. Right. So here, phi is a formula that contains x. Presumably, it doesn't need to, in which case we're saying something that doesn't have much information in it about x. But if phi contains x, we're saying then for all x, the property phi is true. And to prove that's true, we want to be able to prove that phi holds for an arbitrary y instead of x. So the right thing to have here is that what we need to prove here is the formula phi with y substituted for x. There we are. And when we've done that, we've made use of our arbitrary y. It's a bit like an assumption in a sense. I know it's not assuming a logical property, it's basically assuming it's like when you say in a proof, consider an arbitrary y. Then we go down and we say, well, phi holds for y, therefore phi holds for any x. At that point, we've made use of our arbitrary y, so we don't want to use it again. So we're going to put a box around this like we did when we had assumptions. Okay, so this is for all introduction. And if we go back to the proof, we now see that we've proved the property px and qx with our arbitrary y substituted for x. So here, line 7, we can now conclude by universal introduction for all introduction that for all x p, x, and q. Oh, let's go scroll a bit. Fix the p, px, and qx. So this is now for all introduction, and the box needs to go around y. So that's for all introduction from 4 to 6. And lastly, we can conclude the implication because we started off with this assumption. That's the left-hand side of the implication. We've reached what we were trying to show on the right-hand side of the implication. So by our implies introduction rule, we get line 8. We finally get what we were trying to prove. So for all x, px, and all x, qx, let's continue down on this line, implies for all x. Let's fill that, it looks a bit like an exclamation mark, so let's make it not. It's a bracket, so for all x, p this is by implies introduction lines 1 to 7 to 7. Sorry, this was up here a 6, which seems to have turned into a box. And once again, because we're getting rid of the assumption at the top here, we put another box round. Making the boxes nicely nested as they have to be. And there we are. So we have successfully proved the formula we wanted to prove. And we did that making use of the introduction and elimination rules for the universal quantifier. I want to, this looks a bit messy here, so I just want to make sure that's clear that that's a y. Right, I want to point out two things about these rules. Firstly, notice there's not an exact symmetry in the substitutions. For all elimination, you can substitute an arbitrary term in, because phi holds for all x, so for any possible value we can describe, it holds for that value. So terms always describe value, so any term will do. Whereas for the universal introduction, to show that phi holds for all x, we need to show it holds for an arbitrary value, y. And it's not appropriate to use a term, a general term, so every variable is a term, but it's not appropriate to use anything other than a variable here for an arbitrary value, because, for example, if we used a term like y times y, then we would only be showing that phi holds for square numbers, which is not all numbers, if you see what I mean. So it's very important here that this is a variable. It's called the eigenvariable. So y is the eigenvariable. Oh, the eigenvariable seems to work better if I write faster. That's a good thing to know. And we'll see if that really does work. And the point is, this has to be, in some sense, we need to guarantee that this is an arbitrary value. So for that, we need some rules, and these are like typical of the rules that govern boxes. So the rule, what are the rules for the boxes in this case? So box in the for all introduction rule. So firstly, this top line in the box is where y is introduced. In the proof. And an important property we need to require that's associated with that is that inside the box is the only place where y is allowed to occur, the variable y is allowed to occur free in a formula. So the variable y only occurs in the proof free in formulas inside the box. And then also because we want the boxes to be nicely nested, as they were in the natural deduction proofs of propositional logic, we also need to make sure that this box does not contain any open assumptions, because if it contained an open assumption, then we might need to close the assumption using an implies introduction or something like that, and then we would have overlapping boxes. So the box contains no open assumptions. So while we're doing the proof, we're going through the box, we can introduce an assumption, but before we finish the box, we have to close the close the assumption. So we have to use a rule like implies introduction or negation introduction that closes the assumption or discharges the assumption. I was also saying in the lecture on natural deduction for propositional logic. And lastly, it should really go without saying, but let me say it just to be clear. The formula phi with the eigenvariable y substituted for the universally quantified variable x, this needs to be the last line in the box. So phi y x is the last line. Okay, so I've gone over that in quite a lot of detail. Those are the rules for the universal quantifier. So notice this is very similar to what we had for propositional logic. So in propositional logic, for every connective, we had introduction rules and elimination rules. Also for the universal quantifier, we have an introduction rule and which tells us how to derive a formula that has as its outermost logical constant, logical operation, it has universal quantification, and the elimination that tells us what to do if we've proved a universally quantified formula and we want to make use of it. So existential quantification is also going to have, and there seems to be room on this page, so let's do that. So existential quantification is also going to have an introduction and an elimination rule. So let's start with the introduction rule because that's the easier one for existential quantification. So we need to think, what do we need to show? So suppose we want to prove that there exists an x such that phi holds. Oh dear, got rid of the x now. I need to try going up a bit. Let's try drawing fast. Okay, not too bad. It's a very small phi, but it'll do. So if we want to show that there exists an x such that phi holds, well, the normal way one does that is one shows that phi holds for some particular value of x. And how can we describe a particular value? Well, what we've got in the language for describing values, that's elements of the universe, are terms. So as long as we can show that phi holds for any term instead of x, then that's good enough to show that there exists an x, because we've shown that phi holds for some value. So we can just use the substitution, and we need to just show that phi holds for some term t substituted for x. So here this is show phi holds for any single term t substituted for x, and we're done. Then if that holds, then that doesn't look like a very nice t, but well, maybe because I want to make these notes available, maybe it is better to write it a bit more tidily. So there we go. Right, so that's the introduction rule for the existential quantifier. The elimination rule is, however, quite a bit more complicated. So suppose we've, in this case, proved that there exists an x, or assumed, but suppose we have in our proof we know at the moment in the proof, the current state of the proof, oh dear, that was supposed to be an x. There exists an x such that phi holds. Then, So this is a one formula. It looks a bit far apart, but well, it's not as far apart as this one. Anyway, as the formula exists x phi. Well, that's what we've got in our proof, and we want to show that something follows from that. Well, how can we show that something follows from all we know is that there exists an x such that phi holds? So suppose we want to show that psi, some formula psi, follows from that. Well, we can say that phi follows from there existing an x such that phi holds if we can derive psi from phi holding for an arbitrary value of x. So if no matter what value phi holds for, if from that we can conclude psi, then that's enough to conclude that psi follows from there exists an x such that phi. So again, we want to deal with an arbitrary value. Let's call it y. So let's use a variable to talk about this arbitrary value, such that phi holds for that. So this time we make an assumption that phi holds for the arbitrary value y instead of x. So again, for y substituted for x. And if from that assumption we can conclude that psi holds, then that's enough to say, well, okay, psi holds as long as phi holds for an arbitrary value, for whatever value it holds for. So that's enough to say, well, then psi follows as a consequence from there exists x phi. And again, when we do that, we can draw a box around here, and we don't need to use the arbitrary value of y anymore. So again, we have rules for the box here. So the rules are again, so y phi y x. So this is the formula, and this is, we're saying we're introducing the variable y as an arbitrary value into the proof. So this is again is the top line of the box. And it's an assumption. And an assumption. Because we're assuming that. So again, y does not occur free outside the box. So in particular, the formula psi is outside the box. That's the conclusion of the rule. I should have finished the rule, by the way, so let's finish that. This is the existential elimination rule. So the formula psi is outside the box. So in particular, y does not occur free in psi. Again, psi is the last line of the box. And this time, whereas before we had the box contains no open assumptions, here we do have an assumption in the box. But before we draw it, whenever you put an assumption in a box, you close the assumption. But the point is, at this point, when we get to psi, there is an open assumption, but this must be the only open assumption. So then it's closed by the box. So phi y for x is the only open assumption in the box. So it's the only open assumption before you close the box, at the moment before you close the box, and then it's closed by the box. And then it is closed by the box. So once again, while we're doing the bit of proof that has the dots in here, of course we can introduce new assumptions, but before we get to psi, all those assumptions have to be closed. Or by the time we get to psi, all those assumptions have to be closed. And at that point, there's one assumption left, this one open assumption left, and we close that with the box. We seem to have got a circle here. Let's correct that. So this is exists elimination. Right, so a little bit of a complicated rule. So let's see an example proof that uses this rule. And what we're going to do is we're going to prove this, that if so given a unary predicate, so again one argument predicate, so a predicate with arity 1, p, and a propositional constant r, or you can think of it or as any formula that doesn't contain the variable x, in fact, if you want, but anyway, we'll do it with the propositional constant. We're going to prove the following implication. So suppose it holds that there exists an x such that p holds of x and r, then there exists an x such that p holds of x and r is true. The point is, r is just a propositional constant here, or it, as I said before, it could just be an arbitrary formula that does not contain. In fact, let's actually do it in that generality. So let's make it a formula phi. Again, where x does not belong to the free variables of phi. So x is not a free variable in phi. That's what this notation means. Just to have it in the notes, I suppose let's just say x not free in phi. Okay, so if x doesn't occur in phi, we can pull it outside the existential quantifier. Let's make that implication a bit clearer. So again, we're going to start with an assumption, which is the left-hand side of the implication. So we're going to assume that there exists an x such that there exists an x just trying to get an x to look like an x. Let's get up a bit. There exists an x. So, almost seems like the tablet gets tired after a while, or rather the software gets tired after a while. It's probably me getting tired, but it seems to me like the tablet gets more and more, starts to misbehave more and more. So there exists an x, px and phi. That's our assumption. So we want to get this formula that there exists x, px, and outside the existential quantification phi. So we're going to have to work with what we've got, which is this existentially quantified formula. So the obvious tool to use is the elimination rule for the existential quantifier. So we're going to start doing that, and then we've already got here this premise. So we need to start working through this second premise, which means the next thing we need to do is give ourselves an arbitrary y and assume an arbitrary variable y and assume that phi, the property, well actually not phi in this case, it's px and phi holds for y. So here, the second line we give us as an assumption, we'll introduce the arbitrary variable y, and we're going to assume then that this property holds for y. So we need to substitute y for free occurrences of x in px and phi. So when we substitute y for the free occurrence of x in px, that's py. I was going to say that very sloping bracket we'll have to do, but then I decided it was too sloping. Right, we also want to substitute y for the free occurrences of x in phi, but we've assumed we're working with a phi that x does not occur free, and so we substitute y for the free occurrences of x there are none, so we just get the same formula phi back. Okay, so this is another assumption, as it needs to be, in order to make it part of the reasoning licensed by the elimination rule. But now we've got a conjunction, so we can get the separate parts out. So let's take out the left-hand side first. So we've got py. Seems to work better if I work up at the top here. So this is by elimination 1. Maybe going fast doesn't work. Let's try doing it backwards. Okay, and elimination 1 from 2. But if we've got that p holds for y, well, y is a term, it's a variable, so we've got that p holds for some y, so we've shown that there exists an x such that p of x by the exists introduction rule. So there exists exists an x such that px exists introduction from 3. And again, applying the and elimination on 2 on the other side, on the right hand side this time, phi holds. So this is and elimination 2 on line 2. Now we've got exists x px, and we've also got phi, so we can put them together and get the conjunction that we want on the right hand side of our proof. Exists x px and phi. So this is and introduction on 4 and 5. So from our assumption on the left-hand side of the implication, we've got the formula on the right-hand side of the implication, but we can't apply the implies introduction rule because we've got another assumption that we've made in the middle. We're only allowed to apply it to the most recent assumption, but that's because we haven't completely completed our reasoning yet. So this was an assumption that py and phi holds for an arbitrary y. From that, we've shown that from that assumption, exists x px and phi holds. So this is the formula psi in the exists elimination rule, which if we look at it, so the formula psi here, once we show that holds from this assumption, we can discharge that assumption, closing it in a box, and also closing off the variable y for the arbitrary value. So we now, and then the conclusion of the exists elimination is again the same formula psi. So the next step is we derive the same formula psi. So that's again exists x px and phi by exists elimination on 1 and on the block from 2 where we introduce the arbitrary variable to 6. And then we draw, I'm just going to give myself more space by moving this y a little bit to the right. So we draw a box around, closing off that assumption. This is completing the inference by the exists elimination rule. And now we're in a position, all this part's closed off, we've closed off this assumption that we have shown exists x px and phi from the one open assumption there exists x px and phi bracketed differently. So finally we can apply implies introduction, and we get the formula we want, which is that exists x px and phi implies exists x px and phi. So that's now by arrows, by implies introduction from 1 to 7. 1s are 7. And because it's an introduction rule, we discharge the assumption by closing it in a box. There we go. Okay, so that is natural deduction for predicate logic. We're almost done, only there's one more thing we need a rule for, which is we're including equality as a logical symbol, and equality has its own rules for reasoning. So again, they're introduction and elimination rules, and let me introduce you to those. The introduction rule for equality introduction is all you need to do the easiest way to derive an equality is to derive the equality that, well, a term is always equal to itself. So obviously that's not an interesting equality, it's just the reflexivity property of the equality relation as it's an equivalence relation. But what we want the rules to provide are not special equalities that happen to hold because of circumstance, but rather we want the rules for equality that tell us the properties of equality that are guaranteed to hold as its logical properties. So in fact you can't really do much better than, because nothing is guaranteed to be equal to anything else unless there are special circumstances. So the best rule we can have for an introduction rule is really that to show that a term is equal to itself. And then the elimination rule, well, that expresses a nice property of equalities. So if we've got a formula, an equality formula, so it will always be of the form saying that some term t1 is equal to some term t2. Well, the elimination rule says then if two things are equal, then they're somehow intersubstitutable. Whenever you use t1, you can equally well use t2 because they're equal. So if we have any formula, phi, with t1 containing t1, and well, let's mark some occurrences of t1 by saying it's actually some formula phi that contains a free variable x, and what we're interested in is what that formula looks like with t1 in place of x. So suppose I want a nice close square brackets there. So if phi holds where we've got some occurrences of t1 highlighted because they're those occurrences that replace x in the formula phi, then we could replace those same occurrences of t1 with occurrences of t2. And I'm going to end with a proof that, let's see if there's enough space, yes there is. So the proof is going to be a proof that from these rules we can derive the transitivity property of equality. So of course we want equality to be an equivalence relation, that's a basic property of equality. It's clearly going to be reflexive because of this rule. We want it to be symmetric and transitive, and let's derive the transitivity property. So I'm going to do a proof of the logically valid formula for all x, for all y, if and for all z, if x equals y and y equals z, then x equals z. Right, so here the main connectives of the universal quantifiers, the main quantifiers, and then we get down to an implication. So we want to introduce an arbitrary x, y, and z in order to prove the we want to use arbitrary x, y, and z in order to ultimately be able to prove the universally quantified formula using the for all introduction rules. So step one, I'm going to introduce, and actually this time I'm just going to use the same variables. We'll see that that's okay. So I'm going to here introduce arbitrary variables x, y, and z. And we're going to then make the assumption that's on the left-hand side of the implication. So then the assumption is going to be the formula x equals y and y, whoops, and y equals z. So this is an assumption. So it's a conjunction, so we can derive that x equals y by and elimination on the left-hand side, so that's from line 1. And we can also derive that y equals z by, whoops, by and elimination, and eliminate, oh dear, that looks too horrible. I'm really sorry about this. And elimination on the right hand side, also from line 1. Right, so we now want to apply the equality elimination rule to derive that x equals z. Right, so we can take y equals z as the premise t1 equals t2, and our formula phi with t1 replaced, so ignore the x is a bit misleading here. This could equally be well given any name because it's been substituted out by t1. So let's change the rule just to make this neutral, a neutral letter point of that x was we were substituting with t1 and we were substituting it with t2, so it doesn't matter what it's called because it's substituted away. So let's call it w. That's still the same rule. And we're going to make, so here we've got, this is going to be t1 equals t2, so I'm just going to put some notation here, some annotation. It's not really part of the proof, it's just what the work we're doing behind the scenes to check that we're applying the rule. So t1 is, let's put, this is not a formula, this is just saying that the term t1 is, so I'm using this equivalent symbol to make that clear, that t1 is, so t1 is y, t2 is z, and phi is going to be the formula x equals w. So phi is the formula is x equals w. Dvojniva. When I can get one written, there we go, x equals w. Let's put it in brackets just to say the formula phi is this formula. Rather ugly brackets, but never mind, phi is the formula x equals w. Okay, so t1 equals t2 is y equals z. Phi with t1 substituted for w, that's phi with y substituted for w is x equals y. That's this formula here. So what we can conclude from the equals elimination is phi with t2 substituted for w, that's phi with z substituted for w, that's x equals z. So we indeed get that x equals z by equals elimination from, let's put them in the right order. So it's equals elimination from the first premise, the t1 equals t2 is this one, y equals z, so that's line 3. And the second premise is x equals y, which is the formula phi, x equals w with t1, that's y substituted for w. So that's line 2, the second premise. The important thing is we've got the right side of the implication now, and of course in line 5 we can just then get the implication. So that's, we've derived that x equals y and y equals z. Oh dearie me. I really need to find some better way of dealing with this tablet. Still early days, I believe. I mean, it's my second week doing this. So y equals z implies x equals z. So that implication we've got now by implies introduction from 1 to 4. And as always, we close the draw the box around. Ooh, anyway, it's good enough. You can still see. Well, actually, let's get rid of that. Let's try and avoid that. The lines going over the letters. Okay, so we've closed this assumption, but we haven't yet got rid of the x, the y, and the z arbitrary variables. But now we're going to one at a time. First show for all z this formula, then for all y this formula, then for all x this formula, using the universal introduction rules. So line 6, we're going to show for all z. And let me just put these marks in to say that we're taking the formula above. So this is for all introduction from 1 to 5. And so now we draw another box around, and we've now taken z away. It doesn't matter if these lines get very close. Oops, I suppose we want to go down to here. And this is acceptable because this block of proof from line 1 to line 5 did not have any open assumptions because we had closed the assumption on the implies introduction using when we applied the implies introduction in line 5. We closed the assumption, so we had no open assumption, so it was legitimate to take this block and then use up our arbitrary variable z. And in the same way now it's okay to put in for all y. And now we've got so this is by for all introduction 1 to 6. And again, draw another box. So these proofs can be done much more neatly if you have better control over your pen than I've got with this tablet. There we go. And we still have to introduce the x for all x quantifier. Of course, in practice, you would do all these for all introductions in one. You could do them all in one step. I mean, you can see that the reasoning is valid, but to apply the rules as they're written, we only have a rule for introducing. So if we go back to the rule, introduction rule, we can only introduce one quantifier. We only have a formal rule that allows us to introduce one quantifier at a time. So finally, we introduce for all x, and let me write, because it's the final formula, let's write out the whole formula. Z. Oh dear. It's really beginning to look like the handwriting of someone who's a little bit drunk. Or maybe even not such a little bit. Anyway, this is the formula we've derived. Rule by. Oh dear. For all introduction 1 to 7. And again, we need to put a box around which takes all the assumed variables away. And we're done. Okay, well, sorry again for all the problems with the tablet. I really hope I'm going to get the hang of it. I ended up saying the same thing last week, but again, I'm saying the same thing this week. Let's maybe put a big square to end things, and don't really need to do that. Anyway, that's it for this week. You haven't had any exercises to do with natural deduction yet, so the next exercise class, not this week's one, but the next exercise class will involve exercises for natural deduction. Okay, so that's it for today. So bye, and there will be another lecture next week, which I guess will again be a video lecture. We shall see.